Okay, so the extreme value theorem. This is not anything too mind-boggling, except the idea that this has a name. So the name is, so this theorem, this idea has a name, the extreme value theorem, often abbreviated the EVT. So you're going to see that calculus has a lot of different theorems to it, and what you have to pay attention to is what are the hypotheses of the theorem, and what is the conclusion of the theorem. And these hypothesis and conclusion are easily identified by the words if and then. Okay, so the hypotheses are that f has to be continuous on a closed interval AB. So if you don't have f that's continuous on AB, then whatever happens after, well, maybe it will happen and maybe it won't. We don't know. But if the hypotheses are true, then the conclusion has to be true. So, for example, if I have my function f here, and I have a closed interval AB, and my function is continuous, all right, then this function has to achieve a maximum minimum. The maximum is here, the minimum is here, all right? But if I take the same function, and I'm not on a closed interval, so let's say I do this, all right, then I'm really only looking at from here to here. So in this case, f has a max, but it does not have a min, because what should be the min is excluded, okay? So this happened because we're not looking at a closed interval, even though f was continuous. So that could happen, you know, on either side. Here's a half open interval the other way. So now f has a min, but actually in this case, so this is an interesting case, on this interval from, let's call this A to B, this interval that is closed on one side and open on the other, f still attains a maximum value and a minimum value on the interval. So just because we fail the hypotheses doesn't mean the conclusion isn't true. It could be true, all right? But when the hypotheses are not true, the conclusion either might be true or might not be true. We have no way of knowing. But if the hypotheses are true, then the conclusion has to be true. There has to be a min and a max, okay? So the situation I did not draw here is what if f is not continuous? So for example, you know, an obvious example is we could have f that has a vertical asymptote, right? And then we could have a nice closed interval. So here's my nice closed interval, all right? But f has a minimum value. Maybe it has two minimum values. You can have two minimum values if they're equal. But there's no maximum value on this interval because it goes up forever, all right? So now we have a closed interval, but a discontinuous function. So we met this part of the hypotheses, but we didn't meet this part. Therefore, the conclusion might be true or it might not be true. All right, so that's a little bit about the extreme value theorem. And then we have questions about that occur on page 194. So on page 194, we have things where so it says, identify the x value, just the x value, which any absolute value, extreme value occurs. Explain how your answer is consistent with the extreme value theorem. That's what we want to focus on here. On 1 through 4, by the way, it doesn't say that. It just says find the extreme values and where they occur. So this one wants an x and a y coordinate. This one wants an x coordinate and how this accords with the extreme value theorem. So for example, in number 6, so we have a, I don't know if I want to draw these, so look at this. Okay, so what I can see on 6 is that where are their absolute values? Where are their absolute extrema? So there are absolutes, there's a relative min at A, an absolute max at C, and a relative min of B. So we want to say relative min at A, there's an absolute max at B, and there is an absolute min at C. All right, how is this consistent with the extreme value theorem? Well, f is continuous on a closed interval, and both max and min occur, right? Here's a max, here's a min, and we can see that the function is continuous on a closed interval because both endpoints are closed. All right, how about number 8 though? Okay, so is there a maximum value? No, because this would be where your maximum would be, but it's excluded. That's an open, I don't know if you can see it on here, it's an open circle. Is there a minimum value? No, because here where there's a min, there is an open circle. So there's no minimum value either. By the way, if this point were down here, then it would be the absolute min on that interval. All right, but it's not, it's up here. So this is not a max, there's no max and no min. So for number 8, we're gonna say there are no max or min, and this is because f is not continuous and not on a closed interval. Right, it's an open interval. So now we can have this happen if either f is not continuous or f is not a closed interval. It happens in this case that both things are false. So we failed both of the criteria of the extreme value theorem. Another way you can look at the hypotheses is you can think of them as criteria, that if you meet these criteria, then you will have this conclusion. There are actually 2 criteria here. F is continuous and the interval is closed. The theorem will fail to apply if either of the criteria fails. So here's f continuous failing, here's closed interval failing. Here, both criteria failed. They don't have to both fail. Only one has to fail in order for the theorem to no longer apply. All right, we'll just look at the last one, number 10. So on number 10, I can see that actually there is a max at a, because even though the function is open here, well, there's a point right there, and that's clearly the highest point that the function attains. That point a, we don't know the y-coordinate, but they didn't ask us for it. That point at x equals a is the absolute max on this interval, and c is the absolute min, and b is a relative max. All right, so in number 8, we're going to say a is absolute max. B is, C came next. For some reason they put C. Oh, I guess they put C in the middle. These guys are messing with my alphabet. All right, so then C is absolute min, and A is a relative max. That's actually B. See, now I can't even say my ACBs anymore. All right, there you go, ACB. All right, and the reason that's consistent with the mean value theorem is that even though f is not continuous, all right, so in this case, by the way, the interval is closed, right, because f is defined at a. It just has a discontinuity there. All right, so the interval is closed. We have all the x values covered. C, by the way, is a non-differentiable point, but it's still continuous. F is still continuous. But f is not continuous at A. So f is not continuous at A. Nevertheless, f attains both max and min. So that speaks again to the idea that even if I don't meet the criteria, the conclusion could still hold. We just don't know. It doesn't have to hold. In this case, it does. So this is what it means when it says, identify each x value at which any absolute extreme value occurs. Explain how your answer is consistent with the extreme value theorem. All right, so next, we're going to look at some more examples of finding extreme values.